Okay, so let's talk about question number 40 from the assignment from yesterday.
Oh, no.
So, here's the drill. So you have two types of spectrum, and that's what that chart that I have up there on the wall. And we're going to talk about both of them today. You have emission spectrums and you have absorption spectrums. So emission spectrums are more complex. So if you look on number 40, what they're saying is that, hey, these are the allowable energy states that these particles can exist in, typically electrons. So on the emission spectrum versus an absorption spectrum, on the emission spectrum, the electron gets excited to a particular energy level. And then it doesn't like that, so it returns back down. So on emission spectrum, this is why they're more complex. So on an emission spectrum, like if you excite an electron up there to that 7 electron volt line, when it comes back down, it has options. It could go from 7 to 4. So if it goes from 7 to 4, that would be a difference of 3 electron volts, okay? So then the whole task of this is that you're going to try and figure out the wavelengths that are associated with this. So you know that E equals hc over lambda. Use the hc, which is in electron volts, nanometers. So the 3 electron volts is what you're going to have for your E. You're trying to find the corresponding wavelength. So this is the cool part about how you analyze light to figure out what's happening with these electrons. So if you see at that particular photon being emitted at the 3 electron volt line, you can determine, oh, this should be the wavelength of light that corresponds with that transition. It could also go, once it hits 7, it could come all the way down to 2. So that would be a 5 electron volt difference, okay? So on the way down, you look at all these different possibilities. It go from 7 to 4, it go from 7 to 2. It can go all the way from 7 all the way down to 1, which would create a 6 electron volt, okay? So of those transitions, which one is going to produce the shortest wavelength?
7 to 1.
Why?
Because it's the most energy.
Yeah, that's the most energy. So your 7 to 1 jump. So I won't do this because I'm old, but although my chemistry students have seen this, I just don't want to risk my knees. So imagine that I'm within this room. Here I am at the ground state on the floor. So I could be like up on the table. I could be up on a chair, okay? I could be up on a gray table. I could be up on this table, or I could be up on the counter, or really aggressive, I could be on top of the cabinets, okay? So on an emission spectrum, that's going to be caused by me jumping back down. So what would create the biggest scream and me going, God, ow, that hurts, okay? Which one will create the biggest one? Obviously, if I'm going from the top of the cabinets down. If I go from this countertop here to the top of the tables, that's a pretty small value. You just might hear a thump, okay? As opposed to thump out. So even if you couldn't see what I was doing, you could hearing me yell would be equivalent to the photon of light that's being kicked off. So on the way down, you can go from 7 to 4, you can go to 7 to 2, you can go from 7 to 1, okay? Now, if you get to 4, you could go from 4 to 2, okay? That's a 2 electron volt. You can go from 4 down to 1, that's a 3. If you've already done that for the 7 to 4 transition up above, here's the deal. We can't tell the difference what's creating that 3 electron volt light. I don't know if it's moving because it's moving from 7 to 4 or if it's moving from 4 to 1, because the net difference in those energy levels is going to be the same. So 7 to 4, 4 to 1, exact same light. So basically, you got to go through and say, okay, what are the possible combinations? So on emission spectrums, you can come back down in stair steps. So if I'm on top of the cabinet, I can go from the cabinet to the black counter, from the black counter to the table, from the table to the chair, from the chair to the floor. Okay? So I can come down in steps. Now, in contrast to that, and this is what we're talking about today, is what's known as absorption spectrums. So what happens on absorption spectrums is that you shine the entire possibilities of light on the atom. What will happen is that it will, as the name implies, it will only absorb energy to move from the ground state. So on an absorption spectrum, absorption spectrums are simpler. Because on an absorption spectrum, if you have this same thing where you have 1, so there's your 1 electron volt, there's your 2, there's your 4, there's your 7. So on an absorption spectrum, it's like you're going to shine on me all this whole spectrum of energy. So what's going to happen on the absorption spectrum is that if I'm on the ground level, I can only absorb enough energy to go from here, like to the orange chair, from here to the top of the cabinets. I can't be on an absorption spectrum, I can't be on the gray table and then be stationary there and from there move up to the top of the counter. So absorption spectrums are simpler because of the fact that you're only going from the ground state up. You can't have the little sub-steps like you can on the emission spectrum. So on the emission spectrum, you can go from 7 to 4, 4 to 2, whatever that is. Absorption spectrums, you can go from 1 up to 2, you can go to 1 up to 4, you can go to 1 up to 7, and that's it. So you can have much fewer absorption lines. So let me show you what that looks like. Danny, give that a little spin over here. So what this shows you, like here are like the elements, and these are the bright line spectrums. So these are all your emission spectrums. So notice that these, like here's your visible light spectrum for 400 angstroms over to like 7,500. So notice over here on this side where it's your red, notice those are your longer wavelengths. Here's your violets, those are your shorter wavelengths. So what creates each individual band of light, like so if you look at lithium, it's got a line of red, a line of yellow, a line of kind of lavender, and then one of deep purple. So what that means is that lithium, in terms of an emission spectrum, can only make a transition to kick out this amount of energy, this amount of energy, this. That's it. There's only 4. Lithium is a very simple line because it only has 3 electrons. So you can't do a lot with lithium because it isn't very complex. Now, you look at like this one, barium, okay? So barium's way down here. It has like 56 electrons. So it has 56 electrons that can jostle around. So barium has, where's the barium? So barium here, notice it has all these lines. It has all those lines because it has all of those electrons that can jump around and absorb and emit light. So here's the point. The reason that you have bright lines is because electrons are in quantum states. They can absorb a certain amount of energy, they can emit a certain amount of energy. If electrons were in the classical idea, every element would produce a continuous spectrum because that electron could absorb or emit any amount of energy. So if it were classical mechanics and the energy was not in a quantum state, looking at spectrums would be boring because every one of them would just produce a continuous spectrum. And then they said, oh, right, they're different. Why do they only have certain bright lines? Because they only can absorb or emit certain amounts of energy. Now, this is down here, here's the difference. So these are absorption spectrums. So what happens in absorption spectrums is that you shine like the entire light spectrum on the element. And what happens is that you get gaps in here. The gaps are where those electrons are soaking in those photons and making that transition state. It's jumping up to an energy level, and that's why you have gaps. So bright line spectrums, the emission spectrums, they're not very, there's a whole bunch of lines. Absorption spectrums are much simpler because they can only absorb energy coming out of the ground state. Okay? See the difference between the two. So if you have like a comparison of different lines, the emission one's going to be the one that's more complex. So if they say, hey, which one is the emission spectrum, which one is the absorption spectrum? The emission spectrum is going to be the one that's the most complex. Okay. All right, Annie, we're back over here. So on number 40, here should be kind of your range from your wavelengths. They should go from about 200 to about 1200. Okay? So that should be that gap from 200 to about 400. Now, on 42, it's a similar type idea. You got the allowed energies are 0, 4, and 6. Draw the energy levels diagram. All you have to do is go, oh, here's 0, here's 4, and there's 6. Okay, do not make that complicated. That's all you have to draw. Okay, it says, hey, do you understand that these are different energy levels? That's all you have to have. Then you've got what's the wavelength appear in the system's emission spectrum. So because of the fact that you can go from 0, 4, and 6, so because it asks for the emission spectrum. So you could go from 4 to 0, you could go from 6 to 0, you can go from 6 down to 4. So that emission spectrum should have 3 lines. And those wavelengths should roughly go from about 200 to about 600. Okay? What, Charles?
Do we draw those lines, arrows?
No, you don't have to.
Okay.
I'm just showing you that's where it's going to come from.
Okay.
So, yeah, you don't have to draw the lines. But that's, mathematically, you draw the lines, you calculate the values, but that's it. On 45. So, and this is what tends to drive people crazy when you deal with quantum mechanics. So, if you look at 45, you got the speed of an electron is known to be between 3 times 10 to the 6th and 3.2 times 10 to the 6th, which doesn't seem a lot unless you write it out. So you got 3 times 10 to the 6th, okay? So that's 1, 2, 3, 4, 5, 6, okay? And then, which is 3 million. And then you got 3.2 times 10 to the 6th. So you're topping, it doesn't look like much if you put it in scientific notation. Oh, 3 times 10 to the 6th versus 3.2 times 10 to the 6th. Well, if you write it out, you have a difference of 200,000 meters per second, okay? Oh, it's 2 times 10 to the 5th. That's a lot, okay? That's a big gap, 200,000 meters per second. It's like, well, why can't we narrow it down? Again, that's the problem, is that this is this Heisenberg uncertainty principle, is that you're going to sacrifice one thing for another. If you say, well, because by knowing the velocity, basically what we're saying is that you know the high degree of precision what the momentum is. Well, because mass times velocity is momentum. We know the mass. The uncertainty isn't in the mass. The uncertainty is in the position. And the uncertainty is in the velocity, which is reflective of the momentum. So on 45, your unknown value, then, if you look at this in terms of that value, so the uncertainty that you're going to use is that if you subtract these two, if you want to write it as 200,000, if you want to write it as 0.2 times 10 to the 6th, if you want to write it as 2 times 10 to the 5th, I don't care. But that's your uncertainty, that's what's going to be reflective in that momentum part. And so, basically what we're saying then on 45 is that estimate the smallest possible uncertainty in its position, which again looks like your answer is like 0.58 nanometers, which seems like, okay, what's the big deal? Well, on an atomic scale, when you're talking about a single individual atom, 0.58 nanometers is kind of big, okay? But it's just kind of a function of scale. On 54, and this is the one with the photoelectric effect. What's the work function in EVs? What I would recommend that you do, because you've got this graph, and let's talk about this graph. So you've got voltage stop here, and then you've got frequency here times 10 to the 15th hertz. So understand what this graph is showing you. You have frequency times 10 to the 15th hertz. What's that reflective of? The energy of the photon or the energy of the electron? Deacon. You got a 50-50 shot.
I say photon.
You're right, okay? Because this is the frequency of the light that's going to be striking the metal, okay? 10 to the 15th. So here's one of the there's two important things you need to get out of this graph. Number one, this is your voltage stop. This is how much energy it takes to keep Cohen from leaving the jail. So why is there a horizontal line at the beginning?
Threshold hasn't been breached yet.
What threshold?
The threshold of energy that you need to emit an electron.
Or we haven't posted Cohen's bond, right? So here's your electrons, they're moving around the nucleus, they're happy, they're stable, the light's shining on them and they're going, I don't have time, leave me alone, you can't speak my language, you haven't posted a bond, okay? You're showing up to the judge, there's a $500 bond, and you're showing up with $499, and the judge goes, don't care. But I'm close, I'm only $1 off. Judge says, don't care. This is the quantum jail. You either hit the 500 or you don't, okay? So, after you cross that threshold, why is this a linear line? Why isn't it curved? Lauren.
Was all paying attention, what frequency, what's the other thing?
Okay. So why is this a linear function once you cross that minimum threshold to get the electrons kicked off?
What's the Y?
This is your V stop. Can I give you a hint?
Yeah.
Energy of the photon equals h nu, or h frequency.
I mean, I'm forgetting the term, but like there's no, it's not being squared or anything, like it's not,
It's a linear function,
yeah.
okay? So it's E equals hf. There's nothing squared, there's nothing quadratic, nothing. So what that means is if you double the frequency, what's going to happen to the energy of the photon? It's also going to double. So this is why this increase in energy of the photon is a linear function. But remember, the V stop is how much energy you have to stop the electrons. So as you increase the frequency, you're basically giving Cohen more and more and more and more and more money when he leaves the jail. So this point is saying, hey, Cohen, here's $500. You can get out of jail, but you have no money to go anywhere, okay? You can get to the threshold of the jail, and that's it. You have no money to call an Uber, you got no money to get food. You can get out of jail, but that's as far as you're gonna go. Whereas over here, as that frequency gets bigger and bigger and bigger, you're creating more and more excess energy. So mathematically, that voltage stop, remember, equals H times frequency minus your work function. So as HF gets bigger and bigger and bigger, what's that going to do to the work function, Gapshan? Nothing. The work function is a fixed value of that particular material. Okay? It's still going to cost you $500 to get Cohen out of jail. Okay? That number isn't going to change. Well, what's going to happen is that I'm going to bring more and more money to the jail. But I'm only going to have to give $500 to the judge. So as HF gets bigger and bigger and bigger, then what's going to happen to the V stop value? It's going to get bigger and bigger and bigger. Okay? So knowing that on 54, so you've got, use this graph, what is the work function in EVs? So what I would do is that I would go to this graph, let me start over because I've got it all screwed up. Okay? So you got voltage here, which is the same thing as your voltage stop because you're stopping an electron. And then you've got frequency here times 10 to the 15th. I'd pick a certain intersection on the graph, okay? Whatever, just pick a point where you can easily see what your X and Y values are. So this value here is going to be your stopping potential. That's going to be that number. Then you can find your HF, which is the energy of the photon, and from there you can figure out your work function. So if all goes well on 54, and there's some variance on which points that you can pick, but your work function on 54 should be around 4. Okay? If you ever get a work function of like 35, you have done something horribly, horribly wrong. Okay? Big work functions are maybe 5 or 6. So, yeah, don't get big work functions. So, an interesting concept on question number 25, which is about like the whole Star Trek thing. If you've never watched Star Trek, please watch one of them so you kind of know the reference. So, it's, beam me up, Scotty. So, if you've never seen this show, basically what happens is that you have people standing here, and they're in the transporter room, and they get encapsulated in this beam of light, and then you kind of get this swirling effect, and then they disappear, and then on another planet or another ship or something like that, then the beam of light reappears, and then the people show up over there. So the idea being is that, hey, you want to cut down transportation costs, develop, a transporter like this. It's like, hey, Deacon wants to go home, so we're going to put him in the machine. And the idea being is that Deacon is going to disappear because we're basically going to turn Deacon into pure energy. And then we're going to transmit that energy to his living room. And then Deacon, we're going to take that energy and reconfigure it back into matter, and then we're going to get Deacon again. Okay? So you're going from material to energy, and then you're going to take that energy, beam it someplace else, and then reassemble the person. Okay? Which sounds cool. Okay? It does. I mean, that would be cool. Like, you wouldn't have to have a car. It's like, hey, we have a transport room at Mays High School. You want to go home, walk in, boom. Where do you want to go? London, Paris, home, Wendy's, whatever. Okay? And then as long as they had a machine that can reconfigure it, you're okay. But this is where the Heisenberg uncertainty principle plays into account. So, and it's a great concept. It really is, but until you really begin to think about it. So, and it gets a little bit philosophical. So you all have certain memories, okay? It's like, well, where are the memories stored? You know, it's an interesting idea. It's like, okay, you guys probably remember certain things from the beginning of this class. Okay, where's that stored? How do you recall that? So, if you look at just the raw matter, let alone thoughts or memories or anything like that, so you have every electron, every proton, and every neutron that makes you up. So we would have to map every electron, proton, and neutron that makes up every strand of your DNA, every bit of your skin, your eye color, everything, to a very, 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 very high degree of precision to get that part of it. And here's the problem. If you get the position to a very, very high degree of precision, then what are you going to sacrifice?
Velocity.
Or the momentum side of it, okay? Because you can't have both, right? So you can't have both. And so it's like, okay, so then we're going to reassemble Deacon. And I was like, Deacon, dude, your ear's kind of down here. It's like, well, it's kind of, you know, we kind of got that information kind of got transposed a little bit in the system. So, but here's the point. To reassemble Deacon, or anything, you'd have to basically reconstruct it. To reconstruct it, you'd have to have the map. And you can't have a precise map because of the Heisenberg uncertainty principle. So it sounds really cool, okay? It is, like you can transport onto like moving ships and things like that, and it's cool, but all the physicists in the world are going, good idea, we're kind of not going to happen. So, at least on anything that's large, you might be able to do like a single proton or neutron, but anything complex, not going to happen. Okay, any questions on the assignment?
45.
Why is it times 2 on 45?
On 45?
Yeah, 45.
Okay. So you've got the Heisenberg uncertainty principle, right? Which is delta X. H over 4 pi, right? Yeah. Is that how they give it? Because there's different versions of this, whether they use H bar. How does your book list? I think that's how, yeah, that's how your book does it. H over 4 pi. So what you've got then on 45, so you've got, first off, an electron. Well, on your momentum, right? So that's going to be the mass of the electron times its velocity, and then your unknown x. So your uncertainty is not in the mass of the electron. Okay? So that's, you know, that is 9.11 times 10 to the negative 31st. So your uncertainty becomes in that unknown on the velocity. And that's that 0.2 times 10 to the 6th or whatever that you want to use. So there's that value. You know what h is, and you know 4 pi, just solve for x. Yeah.
Yeah, but then
Okay.
we're getting
Yeah,
the half
but
of
then we're
the
getting
answer's
to
supposed to
half
be
of
that.
Oh, yeah, I think the answer in the back of the book is wrong. What do you guys
It's
get?
2.29.
So it's nanometers,
Well, I said,
so it should just be 0.29?
Yeah.
So should,
Okay.
Oh.
so is that,
Okay, cool.
is that like kind of like the radius that can be? Because I thought you could like try and find like
What is it
on either
asked
side.
for?
On either side of it.
Yeah, so that, you're gonna, out of that, you're gonna get 0.29. But then you're going to then, because it's the uncertainty basically on either side of that mark. So that's why it becomes 0.58. That's what they have at the back of the book.
so
So what's
we
right?
do multiply it then?
Yeah.
So we do multiply by 2.
Yes. Alex,
I was not exactly told that we'd have an assignment on Tuesday. Even though I kinda asked about what was going to happen on Tuesday because they'd be testing.
and I recorded the lecture and put the lecture out on YouTube, and at the end of the lecture,
I'm gonna,
there's the assignment.
and so I'm gonna have to
And
go.
that's what I told you to do. Okay, is that cool?
I guess.
Yeah.
Okay,
Man, what do you mean by cool?
I don't know.
Pretty neat.
Kelvin
You
or
understand what's going
Celsius?
on.
Fahrenheit.
We don't use that.
65.
We don't use that here.
Is what
Fahrenheit is not valid.
Danny, stop yonder camera.